All right, section 5-2 is on linear approximations and differentials. And the objective of this section is given the equation of a function f of x, find the linear function that best fits function f at a given point, and then use the linear function to approximate f at other points. All right, so let's talk about a few terms here that we need to know for this section. The first one actually is a term we've used before. It's called local linearity. And the term local linearity refers to the fact that if you zoom in on a function at a particular point, zoom in really, really close on a particular point, that's the local part you're zooming in, that the function will start to look more and more like a straight line as you do that. That's the linearity part. It becomes more like a linear function. So after you zoom in on a point, the function looks linear, is this idea of local linearity. Turns out that if your function has this property of being locally linear, then it turns out your function is differentiable, and vice versa. If your function is differentiable, then your function has local linearity at that point. Okay, now the term linearization, which is actually the topic of this section, they called it the linear approximation, but if you put those two together there, linear approximation becomes linearization, really, of a function. It turns out that the linearization of function is the linear function, which is the tangent line actually, that best fits function f at a given point x equals c. So in other words, when we talk about the linear approximation or the linearization of a function, we're actually just finding a tangent line. And we've done that actually now for quite a bit of time. We've done this actually back to the beginning of chapter 3 when we started finding the equations of tangent lines. So this whole idea is really just kind of a review. We're just giving it a new name. One thing here to note is that the linear function is a close approximation to the graph of f for values of x close to c. And we'll see that with our first example that we look at, that we can use the linear approximation here, the tangent line, to approximate what's happening on our function, our original function f. And you've seen that in some of our sketches where we've sketched the original function and the tangent line. The tangent line comes really, really close to that function right at this point of tangency. And so it does a pretty good job of approximating what's happening right at that one point. And the last thing here, just to recall how we did this back in chapter 2, that if we want to find the equation of the tangent line, we had to find two things. If we're given a point c f of c, and a slope f prime of c. Remember, that's how you find the slope, find the derivative, and evaluate at c, and you know the slope at a particular point. Then you can use the point slope formula, y minus y1 equals m times x minus x1, to find the equation of the tangent line. So we've done that now a number of times. We're going to use that same technique here to find the linear approximation or the linearization of a function. Okay, so let's take a look at an example here to illustrate this. Look at example 1. It says for f of x is equal to, let's go ahead and write that function down. F of x is equal to 15 minus x cubed. And it says find the particular equation for L of x, the linear function, they're talking about the tangent line here, whose graph is tangent to the graph of f at the fixed point 2, 7. Well, that was nice of them to give us both an x and a y value there. That usually we just get an x value, but they gave us the y value as well. And so we want to find the equation there for L of x. In other words, we want to find the linear approximation, the linearization, or that all comes down to finding the equation of the tangent line. So to find the equation of the tangent line, I need two things. I need a point, which they gave us, an x and a y value, and I need to know slope. Slope comes by way of a derivative. So let's find the derivative of this thing. Derivative of 15 minus x cubed would be a derivative of 15, of course, is 0. Minus the derivative of x cubed is 3x squared. So this turns out to be a negative 3x squared. And in particular, we want to find out what the slope is at x equals 2. That's the x value they gave us in this problem to work with. So if we plug in 2, negative 3 times 2 squared, that'd be a negative 12. So we've got the information that we need. I needed to know a point, and I needed to know slope. Once I know those two things, I can use my point slope formula to come up with the equation of the tangent line. So y minus y1 is equal to m times x minus x1. And just plug in the values that we have here. So y1 is the 7, m is the negative 12, and x1 is the 2. In fact, you can leave your answer right there in that form, unless they tell you to solve it for y. They didn't say we had to do that, but I'm going to go ahead and do it in this problem. So I'm going to move the 7 to the other side. So we'll have y is equal to a negative 12 times x minus 2 plus 7. And in fact, I'm going to go ahead and just rewrite this one last time. I'll distribute the negative 12 through there. So you get a negative 12x. It'll be plus 24 plus 7. That's a plus 31. So there's the equation of your tangent line, or as they called it, the linear approximation or the linearization of this function. And actually, they called this L of x, so I'll go ahead and name it L of x there, that the negative 12x plus 31 is L of x. And I'll name it that way just so it'll be a little easier for us to work with this problem here based on using that name, but you don't necessarily have to do that for each of these problems. All right, the next part of this was to show graphically that f is locally linear at x equals 2. So to do that, let's go to our calculator. And again, this idea of local linearity refers to the fact that if I zoom in on this function at x equals 2 in this case over and over again, that it'll start to look more and more like a straight line. So let's punch in the original equation, 15 minus x cubed. And let's graph this in a window. I want to graph this where we're zooming in right on that point at x equals 2, which is x equals 2, y equals 7. So just for ease here, I'm going to go from 0 to 4, so 2 is in the center of my screen horizontally. And we'll go from 0 to 14 so that 7 is in the center of my screen vertically. And we might not get the best sketch of this cubic function, but we do have at least a little bit of a curve to it that we're seeing there. And if you wanted a better sketch, obviously you could zoom out, but what I want to do is zoom in on this point at 2, 7. So if you go to zoom and choose zoom in, and the nice thing about putting 2, 7 right at the center of my screen is that's where the default, or that's where it starts out trying to pick a point to zoom in on. So that's actually exactly where I want to be. So I'll just press enter there. And you can see how our curve starts out as a curve in the first sketch, but now as we zoom in, it looks more like a straight line. In fact, that's pretty straight there. I guess we could zoom in one more time just so you can see that, I'll press enter there again to zoom in one more time, just to see that it's a straight line there. Okay? And this is the idea of local linearity. Zoom in, and it becomes more and more like a straight line. Okay? And in fact, if you were to, let me sketch the tangent line that we came up with, negative 12x plus 31. If we were to sketch that with this original function, let me go back to the original window that we had here, 0 to 4 and 0 to 14, just so you can see the tangent line sketch along with that. You can see how your tangent line, in fact, looks like it shares quite a few points there with our original function around x equals 2. But definitely you can see that there's a difference between those two. But if I zoom in, oops, I want to zoom in. There's my original function and my tangent line. Actually, there's just a couple of points you saw plotted at the very beginning and at the very end, top and bottom of the screen there. So there's a slight difference between points that it plots. In fact, I guess if we zoom in one more time, I don't know if we'll even see any more pixels show up here when they sketch the tangent line there. I did not see any more pixels show up there when you saw the sketch of the tangent line. So in that case, it looks like the tangent line is laying right on top of the original function. Now, I know it's not quite doing that. There's a slight difference between the two, everywhere except for at x equals 2. But you can see how very close they are. All right, it says, in fact, that's what the last part of this says. Now, show numerically that L of x is a close approximation. We can see that graphically here. We're going to do it numerically. To f of x for values of x close to 2 by calculating the error in the approximation. In other words, that L of x is approximately f of x. So to calculate this error, we'll just use our table feature to do that, but let's write down what the error actually is equal to. The error is just the difference between your function and the linear function. So if you calculate f of x at some point minus L of x at the same point, the difference between those is your error, how far you're off. So let's just let our calculator crunch that for us, actually. So go to y3, and I'm just going to use function notation to do this. So y1 is function f, so y1 of x, and L of x is y2, so y2 of x, and technically you can leave out the x's and the parentheses there in this, but just so it looks like function notation, I'll leave it there for you. And let's go to our table to see what the differences are. In fact, I don't really need to see the actual y values. I'm really just interested in the differences. So I'm going to shut off y1 and y2. And let me set up my table here in ask mode. And let's just start to the left of x equals 2, and let's kind of zoom in on this value here. So let's start at how about 1.9. And you can see there's not much of an error there, negative 0.059. It is a decent amount of error, I guess, but not much of an error, not much of a difference between the y values. If we zoom in a little bit further towards 2, now you get really close there. That's negative 6 times 10 to the negative 4th. So that's a really, really small number there. It's a negative 0.0006. In fact, if we zoom in a little bit further, you'll see that that error is even minimized even further. So you can see that as we get closer and closer to 2 from the left side, that error is getting really, really small, which tells me that my linear function and my original function are almost the same. And if you try this from the other side, let's start at 2.1. Again, you'll see that you have a pretty decent error there. Not bad, but it is probably more of an error than we'd want to work with. But if we zoom in on this thing, you can see how quickly you can get closer and closer and closer to this actual value here by looking at the error and the fact that the error is basically non-existent there, very, very small. Okay. All right, let's take a look now at this idea of the linearization of a function. And actually what I want to do is I want to sketch a function and look at the connection between that function and this linear function that we're talking about to get this linearization, and use it to see the relationship between the two, as well as to see the relationships between our differentials, dx and dy, and our changes in x and y, our delta x and delta y, we call that. So let's sketch a function here, f of x. And I want to give myself plenty of room here because there's a lot I want to sketch in here on this graph. So let's say that this is function f of x. And let's say that we're looking for the linearization of this function right here at c. So I can name this point here because it falls on this curve here. I can name this point c, f of c. And when we talk about the linearization of a function, or the linear approximation, those are all words that we use to describe the tangent line of this function. So let me try to sketch in what the tangent line to this curve at that point looks like. And they're calling this in the book there L of x. I'll use the same name here for us so we have some consistency here. But if that's function L of x, realize that it's sharing this same point here at x equals c. So in other words, another name for this point would be c L of c. Not L of x, but L of c. So there's another name that we can use for that point. Now what I want to do is use this linear function to approximate what's happening on function f of x as I wander away from c. So if I wander over here, let's say, this is further than I'd want to wander here, but I'm just going to, just for ease of demonstrating this, I'm going to come over here to x. That if I look at what's happening at x, I can see that at x I get two different values. At c, of course, the two functions were the same. But over at x, they're not. In fact, I can see that on my linear function, I'm at this y value right here. Let's go ahead and name that. That would be x, L of x, would be the name of that point. And this point right here would be x, f of x, would be the name of that point. And again, you can see there's a difference between these two, and that's actually the error that we were just calculating on that last example. In fact, we can go ahead and mark that here, that this distance between these y values right here is the error. That's what we were just calculating. Okay. All right, now what I want to do is look at the connection between dx and delta x, dy, and delta y that you've seen now going all the way back to the beginning of chapter 3, actually, when we first looked at a derivative. And the delta x and delta y, let's start with those. That if I were to calculate delta x, the way you do that is it's a change in x value. So if I just measure this distance horizontally between these 2 points, that's what we call delta x. The difference between the x values on my original function, so I've got 2 points there on my original function, that's the difference in the x values right there is delta x. And then if I measure the vertical distance between these 2 points, so that would be the distance from up here down to here, that's the delta y. So delta y measures the vertical distance between those points on my original function f. Now that is similar to, but not quite the same here, as dx and dy. So if we were to measure dx, dx again is the difference between the x values on my linear function now, my tangent line. So that would be this distance right here, which notice that's the same as delta x. So the nice thing about dx and delta x, they are the same. That won't be the same will not be true for delta y and dy. Now dy is going to be the difference in the y values on my linear function. So that's going to be this distance from here to here. This is dy. So you can see that dy and delta y are not the same. However, if I were to stay closer to c, the closer I stay to c, the closer these two values are going to be. All right, and that's the whole idea, that as long as I stay close to c, the dy and the delta y are very similar. As I wander further away, they're not. All right, so let's talk about how we can calculate each of these quantities here. So some formulas that we can use to calculate these linearization quantities that we're looking at. Let's start out with the delta x and the delta y and the dx and the dy. It turns out that delta x and delta y are related to dx and dy, but they're not exactly the same. We saw that in the sketch. The dx and the delta x were the same, but the delta y and the dy were not. It turns out then, if I take the limit as delta x goes to 0, in other words, the difference between these two values here, if I force, in essence, x to get closer and closer to c is really what's happening when delta x goes to 0. Here's my delta x. As he goes to 0, that forces x to get closer and closer to c. And so when that happens, if I take the limit as delta x goes to 0 of delta y over delta x, that's a limit of a difference quotient. And we learned that the limit of a difference quotient is just another way to describe a derivative. So that's equal to dy over dx, which dy over dx is a derivative. All right. The second calculation here, I guess the second two here, which are really the next two, I should say, that are the easy ones to calculate because these are the same. Dx and delta x we saw in our sketch up above were just the differences in the x values. So from up above, if I scroll up here, I can see the delta x and dx are just the difference in the x's here. So if I take x minus c, that's going to, of course, give me this dx or delta x. All right, the next one here is dy. Now remember, dy is the difference in the linear function values, the difference in the y values in my linear function. So if I take the linear function at x minus the linear function at c, that should give me dy. Let's go back up here so you can see where that calculation is coming from. So here's dy over here in green. And you can see that I'm measuring the difference in these y values to find dy. So I'm taking this y value right here, which is L of x, and I'm taking this y value over here at c, which is L of c, and the difference in those is going to give me dy. That's what we have here. And the next one, of course, is the delta y. Now the delta y is measuring the difference in the y values on your original function f. So it turns out that's equal to f of x minus f of c. And it's a similar calculation. If I scroll up here to our graph again, similar calculation to what we just saw for dy, except it's delta y. So if I take the change in this y value right here, which, let me scroll up so you can see that, that's this y value, f of x, and the y value over here, which is f of c, difference in those two, f of x minus f of c, is in fact going to give us delta y. And the last one here is the error then. And again, there's actually a couple ways. So actually, there's a couple ways you can calculate each of these quantities, but there's a couple ways you can calculate the error. Here are two of them. One way to do it is look at the difference in delta y and dy. So if I scroll back up here so you can see that, the delta y is that vertical distance in blue. Dy is that vertical distance in green. So the difference in those two leaves you that vertical distance measured in red, which is the error there. And the other way that you can measure this in terms of function f and the linearization function L is if you take f of x minus L of x. The difference of those will give me the same result there. So again, this vertical distance here in red, that error, if I take this y value here, which is f of x, and subtract this y value here, which is L of x, the difference in those two is going to give me the error. All right. So that's how we can come up with each of those values there. And we're going to look at an example now that is going to ask us to do that. So look at example 2. For example 2, it says if f of x is equal to the sine of x, to write an equation for the linear function L of x, that's our tangent line, that best fits at x equals 1. So they gave us a point here at x equals 1. Now they didn't give us the y value, but that's all right. We can calculate that here. F of 1 would equal the sine of 1. And I'm going to go ahead and leave it just like that. If you want to punch that in your calculator and get a decimal approximation, go ahead, but it's not going to be a nice number, so I'm going to just leave it like that. So I've got an x value, a y value. I just need a slope. So find the derivative. Derivative of sine is cosine of x. So f prime of 1 is equal to the cosine of 1. So there's our 3 parts here in essence that I need. I need a point, which is an x value and a y value, and I need a slope. And so from those 3 things there, we should be able to come up with the linearization or the tangent line for this function. So let's just do that over here to the right. So we have y minus y1 is equal to m times x minus, x1. Does happen to be 1 here in this case, but I want it as x1. And I'll just substitute in what we know here. We've got y1 is equal to the sine of 1. Y minus the sine of 1 is equal to m, which is the cosine of 1, times x minus x1, which is 1. And again, you could leave it in this form here, but I'm going to go ahead and solve this for y. Y would equal the cosine of 1 times x minus 1 plus the sine of 1. And I'm going to go ahead and just leave it just like that. If you wanted to multiply the cosine of 1 through the x minus 1, go ahead and do so. But there is our equation of this thing. Okay, that's our linearization. That is what L of x is equal to. Okay. All right, so let's see what they want us to do next. It says use the linear function to approximate f of 1.02. In fact, let me go ahead and name this here. This is L of x in our problem, just so we can use that for the rest of this problem. So they're saying to approximate f at 1.02 by using the linear function. So in other words, what they're telling us is that f at 1.02 is approximately equal to L at 1.02. And we saw that in our sketch, that as long as I pick values of x that are close to, in this case, our c value of 1, turns out that our linear function was very, very close to our original function. So let's go ahead and punch that in our calculator and see what we get for L at 1.02. Oops, let me bring up a calculator. And in fact, let's go ahead and put in the original function. We'll probably want that sine of x. And let's put in our linearization here, which was the cosine of 1 times x minus 1. That's just our tangent line here, of course, plus the sine of 1. Oops, don't need that parenthesis. I'll shut off y3 there for right now. I don't know if we need it, but I'll just leave it in there. And the question is, what does my linear function equal at 1.02? So we'll take y2 and evaluate it at 1.02. You could use your table to do this as well, but it looks like we get 0.8522. Let me round this to 5 decimal places because these are going to be really close numbers here. 0.85228. 85228. And you might need to do that for some of these problems that because you're working with some numbers that are so close together, you might want to include a few more decimal places just so you can see how close these numbers actually are. All right, the next part of this question says, what is the error in this approximation? So we're just going to go back and do those calculations we just had written down here. We're going to use a calculator, of course, to help us out. So let's write down how we calculate the error. The error is just the difference between my function value and my linear function. So this is going to be f of 1.02 minus L of 1.02. And let's just use our calculator here to do that. So if I grab y1 at 1.02 minus y2 at that same value of x, 1.02, we get a very small number here, negative 1.69 times 10 to the negative fourth. So that's a really small number. It's a negative 0.000169. So a very, very small error. It's very close to the actual function value. They also ask us to calculate dx, dy, delta x, and delta y. So let's start with dx. dx, remember, is just the difference in your x values here. So our x value is the 1.02 minus our starting value was c equals 1 there. So the difference in those gives me 0.02. So a small change in x for us. That's the change in the x's for my linear function. And then they also ask for dy. So dy is the change in the y values on my linear function. So that's going to be L at 1.02 minus L at 1. And again, I'm going to use the calculator to have it help me do that. So function L is y2. So there we go. And we get a very small change in y here for us. So it's 0.01. I'm going to use several decimal places here again. 0.010806. Okay. Just because our value for delta y is going to be really small as well, we'll see. And then the next value they want me to calculate is delta x. So delta x, again, is the same as dx. So actually, I can just write that down. But remember, it's the change in the x values on our original function. So that's the 1.02 minus 1. That's why we get the same result for both dx and delta x, because they're the same calculation. And the last one that they want me to calculate here is delta y, which delta y is measuring the difference in my original, my y values on my original function. So that's f at 1.02 minus f at 1. And again, let's use the calculator to have it crunch those values for us. That's in y1. And we get, again, a very small value here, so 0.010637. 0.010637. And you can see that the difference in your delta y and dy there are very, very small. In fact, those are the exact same, that difference is the exact same as our error, remember. That's another way we can calculate the error. All right, the last part of this one says to sketch a graph that shows these quantities, which we just did really here on that previous sketch, so I'm not going to worry about sketching this one again. You can refer to that previous work to see that. All right, and that's the end of this section here for us.